Okay, in my last lecture, I was giving you the photoelectric equation proposed by Einstein, which is given by E equals to h nu, the work function of a metal plus the kinetic energy of the ejected electron. And I have mentioned Ke max. What does it mean? This is the maximum kinetic energy possessed by an electron. As I said, the experimental setup is something like this. If you remember, you have a vacuum tube like this, then you have two electrodes, emitter and collector. Let's say this is emitter, this is collector, and you have a power source, let's say, and some current will drive in this. Then the incident light is falling on this electrode. The electrons will emit out in this direction. They reach the cathode. Now, as I said, all the electrons will not have the same kinetic energy. Each electron will have different kinetic energy, and the energy, the maximum energy possessed by an electron is represented here. This is the energy possessed by the electron which has its maximum value. So only then you can equate these two values. So h nu is the photon energy, the light energy that is incident on the electrode, and phi is the work function, the minimum energy required for the electron to come out of the material, and the remaining amount of energy, according to the law of conservation of energy, the remaining energy will be converted as kinetic energy of the electron. Now in this case, let's say the electrons are coming out and reaching the cathode, and a complete circuit is given here. There will be a current I in this circuit. What happens when you apply a voltage here, V? If I apply a voltage, a positive voltage, what happens to the current in the circuit? If I plot a graph like this, the applied voltage and the photocurrent, what happens if I increase the voltage? We all know that electrons, the more number of electrons will reach this electrode and more current will be formed, more current will pass through this circuit. So we can directly, suppose initial photocurrent is this, then if I increase, the current will increase like this till certain voltage. What happens after that? If you increase beyond that, then after some time the current becomes a constant. After some time, current becomes constant, even though you apply the voltage more than that. At particular value, till this value, the current will increase, and beyond that, how much ever you increase the voltage, the current remains constant. Why? Because when you are applying this voltage at this point, all the electrons that are coming out have sufficient energy to reach this electrode. So all the electrons will reach this electrode, and all the electrons will complete the circuit, will travel in this. The current will be because of the electrons that are coming out from the metal, because of all the electrons that are coming out of this metal. So all the electrons are having sufficient energy which are capable enough to reach this cathode, so they form a complete circuit. Then current cannot go beyond that, because all the electrons are now reaching this electrodes. So there are no more electrons. So current will get saturated. So maximum electrons are coming here, and that is the saturation level. So you increase the voltage beyond that, there will be no change in the current. So current remains at the saturation level. That's why current remains constant. Now what if you reduce the voltage? What happens? If you reduce the voltage, how does this graph look like? What happens to the current if I reduce the voltage? If I go towards this hand side, like suppose this is 0. If I go towards the negative axis, negative x-axis, what happens? If I reduce the voltage, then obviously the current will decrease and finally becomes 0 at one particular voltage. At particular voltage, at particular negative voltage, the current becomes 0. I mentioned that this voltage as V0. Why I have given that V0, I'll tell you in a while. But what do you mean by this negative voltage? What do you mean by this negative voltage? It is nothing but I'm just reversing the polarity. That's it. Just reversing the polarity. Suppose initially if I am using like this, if this is cathode, if I am connecting battery like this initially, then I'll just reverse the polarity. I'll do this. The voltage polarity is getting reversed. That's it. So negative voltage means I am reversing the voltage. So what happens when you reverse the voltage and increase this magnitude? Then the photocurrent slowly decreases, and at one point, at one particular voltage value, the photocurrent will become 0. So that particular voltage V0 I represented here is called as stopping potential. The stopping potential V0 is the voltage required to stop the electric current in the circuit. So this amount of voltage has to be applied in order to stop the electrons to reach the other electrode, so that there will be no current in the circuit. So further you decrease, no use, the current will be 0. You decrease the voltage further, the current will be 0. No current will flow in the circuit. This particular voltage, as I said, it's called stopping potential. Why this name stopping? Because current stops. There is another name for this which is called as retarding potential. Retarding potential. You can say either stopping potential or retarding potential, which is represented by V0. So, what do you observe here? As I said, the electrons which are coming out from this electrode will have a kinetic energy. Let's say that electron is having its maximum kinetic energy. So its velocity is maximum compared to the velocity of other electrons. So let's say this electron is possessing the maximum kinetic energy. Now, what I'm doing here, I'm just stopping this electron to reach the other end. If I'm applying a potential which is sufficient enough to stop this electron, then no more current will flow in this circuit. The other electrons automatically they'll stop, because already the energy will be sufficient enough to stop this electron which is having the maximum kinetic energy value. So if I am stopping that electron, the other electrons automatically, it is understood that they also cannot reach the other end. So ultimately there will be no current. So what I am doing when I am using this potential here, when I am applying this negative potential, so I am applying some negative force. Negative in the sense, I am applying a force in the opposite direction to the direction of motion of this electron. I am applying a force using this potential, using this electric source. And that force is actually retarding this electron. It is actually retarding this electron. Now what is the magnitude of that force, or what is the magnitude of energy of the electron? How much work is done by that force? How much work is done by that retarding force? How do we calculate? It is just EV0. EV0. What is EV in general? 1 electron volt represent what? 1 electron volt means it is the electron energy possessed by an electron when the electron is accelerated through a potential difference of 1 volt. Suppose I have 2 points which are at a potential difference of 1 volt, and 1 electron is being accelerated through this potential difference. Then the energy possessed by the electron is said to be 1 electron volt. Suppose if the 2 points are maintained at 2 volt difference, then energy possessed by the electron will be 2 electron volts. Suppose the 2 points are maintained at V0 potential difference, then the electron energy will be EV0. So in order to stop this, you have to provide sufficient energy, enough energy, which is equal to its kinetic energy. And therefore, this energy is equals to half mv max square. This V max again represents the maximum velocity of the electron that is ejected. So when I'm referring to this electron, this is the V max is the velocity of this electron, the most energetic electron. So I'm equating EV naught to half mv max square. Sorry, this is the kinetic energy possessed by the electron, half mv square, and this energy is equals to EV naught. Only when these two balance, then we are making sure that the electrons will not reach the other end and the current in the circuit will be zero. We guarantee that the current in the circuit will be zero when EV naught equals to half mv max square. Now go back to this equation h nu. So can I represent this Ke max from this equation? I can write Ke max equals to h nu minus phi, where phi is the work function of a particular metal. Then I'll write EV naught. This half mv square is nothing but Ke max. So EV naught equals to h nu minus phi. Then what is phi? Can I write phi in terms of Planck's constant and frequency of light? Yes, I can write it. H nu minus phi can be written as h nu naught. What is this nu naught? In my previous lecture I told this nu naught or f naught. I can represent frequency by these two letters, either nu or f. So nu naught or f naught, these are the threshold frequencies, meaning this is the minimum frequency of light that is required in order to eject an electron from a given metal surface. So this is the threshold frequency. So phi, work function of the metal, can be given as h nu naught. So if the frequency of light is just nu naught, then h nu naught equals to phi. Then if the frequency nu is greater than nu naught, then h nu equals to phi plus the remaining amount energy will be converted as kinetic energy, Ke max. This is what we have observed. So nu naught is the threshold frequency and h nu naught is the work function of the given particular metal. So I can write it like this. Then what I can do is, here h into nu minus nu naught. Take h common outside. EV naught equals to h nu minus nu naught. Then we can understand that your stopping potential is proportional to the frequency value, the frequency of the incident light. So from this I can draw one more graph. This is for frequency of the incident light and this is the stopping potential. If I draw a graph, you can see the linearity here. This V naught equals to h times nu minus nu naught. It is linearly proportional to nu. This is just like y equals to mx plus c, a straight line equation. So you get a straight line like this. When you plot a graph between the frequency of the incident light and the stopping potential, the graph will look like this. What will be this minimum value? This you can term it as nu naught. It is the threshold frequency. Means when the threshold frequency, at this frequency, the stopping potential, the potential that is required to stop the electron is 0. Why? Because when the frequency of light is exactly the threshold frequency, then the kinetic energy will be 0. There will be no kinetic energy for the electron. The electron just come out of the material and just stay there. They don't have sufficient energy to go out with some velocities. So the kinetic energy of that electron will be 0. So then no potential is required to stop that. They are already stopped. No need to stop the current in the circuit. So therefore the stopping potential at the threshold frequency is 0. As you increase the frequency from here, you need some energy to stop the electron, because as you increase the frequency, the remaining frequency will be converted as kinetic energy, and that kinetic energy of the electron, in order to stop that electron, you have to apply sufficient stopping potential. So finally, the current in the circuit will become zero. Our whole idea is we are making the current in the circuit zero. And when will you do this? When the stopping potential, when you apply a potential which is sufficient enough to stop the most energetic electron. EV0 is half mv max square. When you apply this potential, then the electrons are guaranteed that they will not reach the other end, so that they cannot form the complete circuit and the current in the circuit will be zero. So this is how it goes. So if I plot a graph, I have shown the graph between the intensity and the photocurrent. Now if I maintain the frequency constant for the incident light, now increase the intensity of light, what happens? The intensity of the light and the photocurrent, it will increase like this. I have shown this in my previous lecture. The intensity of light and the photoelectric current, they are directly proportional. More intensity, more number of electrons will come out. More number of electrons means more charge constitutes more current. So they are proportional. So all these three graphs are very important when you are studying this photoelectric effect. What happens? Suppose this is at a particular frequency. This graph is given at a particular frequency, let's say f1. What happens if I increase the frequency, f1 or nu 1, let's say. This is nu 1. Let's say for the same material, I am now increasing the frequency of light. I'll apply some other frequency, nu 2, which is greater than nu 1. Then how will this graph look like? It just come like this. This is for frequency nu 2. This is another stopping potential. This is 1, this is 2. If you have another frequency, then it will come like this. Nu 3. So nu 3 is greater than nu 2 is greater than nu 1. So what does it tell? As you increase the frequency, the stopping potential that is required to stop the most energetic electron is continuously increasing. So if you increase the frequency, the kinetic energy of the electron will increase, and when kinetic energy of the electron increase, you have to increase the stopping potential in order to stop that. The stopping potential will also increase. In the negative side, as I said, the polarity is being reversed. If you see this negative and the electrons also having negative charge, they have a repulsive force. And if you apply more negative charge, then the repulsive force increases, and finally the energy will not be sufficient. The kinetic energy possessed by the electron will not be sufficient to overcome that repulsive force, and they cannot reach this end. This is how we block the current. So these are the important graphs that we have studied so far. One is stopping potential versus, applied voltage versus photocurrent, then stopping potential versus frequency, and this we know intensity versus photocurrent. More intense light, more photocurrent, we'll see. Now all these three graphs, as I said, could not be explained using the classical laws of physics. In my very first lecture, I have said that these graphs were the experimental results that I have shown. When people did experiments using this experimental setup, the results they have plotted like this, the exact same results they have observed. And the classical theory fails to explain these graphs unless Einstein came up with the photoelectric equation. This photoelectric equation explains all sort of these graphs. So what concludes that? So here we are treating light as a particle. Each particle having an energy h nu, and that particle we call them as photons. And in classical wave theory, we treat light as a wave, classical wave. The classical wave was not sufficient to explain all these graphs. As I said, in classical wave theory, what happens? If the intensity of light increases, the energy will also increase. Then if you apply that, even though you increase the intensity, the frequency being less than threshold frequency, how much ever you increase the frequency, intensity of light, the electrons will not come out of the material. But classical theory says you increase the intensity, the energy of the light will get increased, and the electron has to come out, but it is not happening. The kinetic energy of the electrons that are coming out, they are only depending on the frequency of the light, not on the intensity. More frequency light you use, more kinetic energy of the electron you'll observe. It is not depending on the intensity. Classical theory also says that there is nothing like threshold value of frequency in classical theory. The classical theory doesn't predict that. But here you have a threshold value for frequency. Then, if you illuminate a substance with longer period of time, even though the small intense light will also be sufficient enough to transfer energy to the electron. If you are exposing this electron to the light having low intense light for a longer period of time, some hours and days together, then also an electron has to come out. But there is a contradiction. The electrons are coming out instantaneously when you shine light on it. Instantaneously. Just within 1 nanosecond or 10 nanoseconds, the electron come out of the surface. It is not like electrons are taking longer and longer time, they're trapping the energy of the light for a longer period of time and coming after 1 or 2 days. It's not like that. Within a seconds, nanoseconds, they're coming out. It's a very instantaneous process. So all these things classical theory failed to explain. So this was the beginning, how we treat light. Instead of a wave, we are treating light as a particles. Light is made up of particles. But that doesn't tell that classical theory is completely wrong. For explaining interference, diffraction and polarization patterns, you have to have a wave theory. With wave theory, you can explain diffraction, polarization, all these phenomena. With particle theory, you cannot explain. But this photoelectric effect, you can explain only using particle theory. Can't be explained using wave theory. What does this conclude? It says that light is behaving in a strange manner. It is acting both like a wave as well as a particle. So scientists have concluded that light must be both. It must behave both as a particle, as a wave, depending on the situations, depending on the interactions with matter. It may either behave like a wave or behave like a particle, depending on the interaction of matter. So they concluded that light is something which acts both as a particle, as a wave. Of course, if we go to higher studies, it is even more complex to understand light. But at this stage, we conclude that light is having both particle and wave nature, which we call that as a dual nature of radiation. Dual nature of radiation or dual nature of light. Dual nature in the sense, it is having both particle as well as wave nature. This was a conclusion made by these people during that age. Then, another scientist whose name was Louis de Broglie, he gave a new suggestion. Since the whole universe is made up of two entities, one is light, another is matter, only two entities. The whole universe is made up of light and matter. Since light is behaving both as a particle as well as a wave, he gave a proposal that matter should also behave in the same way, which means matter should also behave both like a particle as well as a wave. Matter is something with everything, matter which has mass and volume. We can treat everything as matter, all the macroscopic bodies, microscopic objects, electrons, protons, everything is matter. So he proposed that since light is exhibiting this special kind of property, matter should exhibit this property, dual nature. And he gave a famous relation for finding the wavelength of matter, lambda, which is equals to h by p. The Planck's constant, and p is the momentum of the body. Here momentum comes where? In the particle nature. When we treat an object as a particle, it has got enough velocity and it has got enough mass, and mass into velocity gives momentum. So when you treat an object as a particle, it has got some momentum. When you treat something as a wave, it has got its own wavelength and frequency. So this is the connection between particle nature and wave nature. You see lambda and momentum. There is a connection between these two. So he derived this using his ideas. So finally he concluded that matter also exhibits dual nature. It behaves like a particle as well as a wave. But all the macroscopic objects, we cannot see the wave associated with them. Why we don't see? Because the momentum, as you can see, the momentum is in the denominator. The macroscopic bodies have huge momentum. The mass is more compared to the microscopic or particles. The microscopic, when I say, the subatomic particles, electrons, protons, neutrons, all these, etc. So electrons, when you compare, suppose if I take a 1 kg ball and one electron, mass of one electron is how much? 9.1 into 10 power minus 31 kg. 1 kg ball and 1 electron. You put those values here. Since this value is very less, very less, you can easily find a wave associated with the electron. Same as protons for other particles which are having lower masses. But if you treat this, if you take 1 kg here, the wavelength will be in the order of 10 power minus 20 or minus 30, in that range. So in that range, you cannot see a wave associated with the macroscopic bodies. That's why we don't see any wave-like nature in the macroscopic objects. But in general, for all the matter, this equation is valid. The wavelength associated with any body can be given as the Planck's constant divided by the momentum of that body when object is in motion. So this is the famous formula given by Louis de Broglie. So this is the first equation, photoelectric equation. This is the de Broglie wavelengths. So these are the two equations based on which we'll be doing numericals for this course. So the next exercises will be based on these two equations. So we'll do exercises in the next upcoming lectures.